So welcome everybody. So today's lecture will be on reduced density matrix functional theory. And my plan is to give you a brief introduction just using slides, and then the rest I will use the whiteboard, okay? So as usual, you can interrupt me if you don't understand, and Emmanuel will keep an eye on the chat if you want to ask questions. So this introduction is just to set a little bit the frame, since we went a bit back and forward between wave function based methods and functional theories. So I want just to set the stage for RDMFT. So as usually we have the many body Hamiltonian for the description of the electrons in a system, and we want to solve our stationary Schrödinger equation, okay? So the Hamiltonian is within the Born-Oppenheimer approximation, is without relativistic effect. So we have the kinetic energy, then we have the electron-electron interaction and an external potential. In this case, I use it a local external potential. And from the many body wave function, we can calculate then the observable. So at the end, we are interested essentially in the observable, which characterize a system. So how do we do this? Well, there are several ways to do this, and here I will focus on ab initio theories. So there are two classes of these ab initio theories that we have seen in this school. Are the one which are based on wave functions, so the key quantity is the many body wave function. So we try to approximate it as at the best we can, and then from it we can calculate the observable, just averaging over the many body wave function. And then there is another class of theories, which are the functional theories, in which one avoids the use of the many body wave function, which is anyway a complicated object, and looks rather at simpler physical quantities. And an example is the density, moving in some effective potentials, and then the observable of this in this theories, the observables are obtained as functionals of this basic quantity of the problem. Okay, so of course it seems that the task now, which is to calculate the basic quantity of the problem, is much simpler than calculating the many body wave function. However, the complexity of the original problem are hidden in this effective potential and in the way in which then we extract the information from the basic quantity of the problem. And here are hidden the so-called many body effects of the system. Okay, so we don't know these things in general, and we need to find approximations. Of course, you have several basic quantity that you can use. From the simplest one is the density. It depends on here. For simplicity here, I don't write the spin. I will do later during the lecture, okay? I will take into account the spin. So here is just to give an intro. So we have the density, which depends only on 3 special variables. Then we can a little bit, of course, the density is simple itself, but then to extract information is not that simple, okay? So you can then decide to increase a little bit the complexity of the basic quantity of your theory, so then it's easier to extract information. So for example, from the scalar, you pass to a vector, which is here the current. This is a vector. You can complicate a little bit more the basic quantity, including another spatial variable, and you have the one body density matrix. You can go further to include some time differences. We have the one body Green's function, so on and so forth. And of course, then it becomes easier to extract information from this basic quantity, but becomes also more complicated, more computationally heavier to calculate them, okay? So we saw that Julien has introduced density functional theory. The basic quantity is the density. Current DFT is very similar. We will not treat it in the school, but it's very similar to DFT. And then what I will treat today is reduced density matrix functional theory, which has as basic variable the one body density matrix. So I like this slides, which was proposed by Hardy Gross in one of his lectures on RDMFT. So I like to repropose to you because it condensates a little bit the links between this functional theory. So if we have the many body perturbation theory, the basic quantity is the one body Green's function. The one body density matrix can be obtained from the diagonal part in the time of G. And then from the diagonal part in space of gamma, we can obtain the density. So they are linked. And they are linked also in the philosophy. Here to calculate the basic quantities of the problems, we have to find approximation to either energy functionals or to some effective potentials. Here is the self-energy in the case of the Green's function. We will see that in RDMFT there's no potentials, there's only the energy functional that we will minimize. And in DFT we have both. Let's say that approximations in many body perturbation theory are relatively easy in the sense that the self-energy can be in principle systematically improved. In RDMFT are a bit more difficult, and in DFT I find very difficult because we have to find in general, we have to find approximation to this quantity which enters the conscious systems, which is not a physical system. So physical intuition is a bit ruled out here. On the other hand, to calculate the one body Green's function, in general, the calculations are heavier than to calculate RDM, the one body density matrix or the DFT. So far, this is for the calculation, for the calculation of the basic quantity of the problem. Once we have it, then we have to extract the information. So we want observables, okay? So how easy is to extract information from this basic quantity? Well, let's say that it's relatively easy from the one body Green's function. If you think about photoemission spectrum, it comes simple like that. In using the one body Green's function is a bit more difficult in RDMFT, and I found very difficult in DFT. So RDMFT in a nutshell is based on this. So you can prove that there is, for a non-degenerate ground state, there is a one-to-one mapping between the ground state wave function of your system and the density, one body density matrix of your system, okay? And this is enough to set a functional theory based on one body reduced density matrix. Okay, so this means that all the observable can be expressed as functionals of gamma, and in particular the total energy, which has several contributions, of which only this needs approximation, as I will show you. So essentially what we do, we minimize the ground state energy, and the exact density matrix minimize the ground state total energy is obtained at the exact density matrix. Okay, so that's it. And then the program that I have in mind for the lecture is the following. So I give you some preliminary, some notations, okay? Then I show you the Hohenberg-Kohn theorem for non-local potentials, which is the basic theorem of this one-to-one mapping between ground state wave function and one body density matrix. We pass through energy minimization. We speak about some approximations to the energy functionals. We see if we can get to the observable, and if I have time, I show connection with the Green's functions that will be the subject of the next lectures. Right, so now I stop the share up and I share the whiteboard. Okay, so we start with the many-body Hamiltonian of the system again. So we have our many-body Hamiltonian. It has the kinetic energy operator. It has our external potential, and it has the electron-electron interaction. Okay, so I will use the notation of second quantization. This was already introduced by Emmanuel. So I will write T as in terms of field operators, okay? So these are field operators, which are related to creation and annihilation operators in a basis set. Then I have an external potential. And now so far with the lecture of Julien, you saw that the external potential was a local external potential. So now I will consider more general potential, which is non-local in space, okay? And this allows me to set the framework for RDMFT. So I have that this is field operators again, my external potential. Okay, and then I have the electron-electron interaction. Which is set like this. This is the Coulomb potential. Okay, where now X includes both the space and the spin variable, and where integral in the X, it means integral in the space and summation over S, okay? Right. Now, given this Hamiltonian, we can now define the n-body density matrix. And I will actually then body reduce density matrix, and I will indicate them like this. Reduced density matrix, okay? So the definition, let's see if I can remember up, is like that. Then I have in a second quantization. Okay, so it's a string of field operators, right, where this is the ground state wave function, okay? And this can be written in this way. There is a prefactor, which takes into account the action of the field operators on the wave function. And then we integrate everything starting from n+1. Up to n, which is the number of electrons in the system. So let me be more general here. I don't like to put the ground state. Let's be more general. Okay. N prime, and then here I have xn+1 up to xn, and then I have x1, xn. Okay, so this is a general definition of the n-RDM, okay? Then of particular interest for our lecture, it will be the two-body one, so n equal 2. Okay, which is this. Okay, so I integrate starting from 3. X1, x2 prime, then x3, xn. Okay. And then it will be the one body that for simplicity in the following, I will indicate like x prime. I forgot to put the expression of gamma 2 in terms of field operators, but okay, it's not a big deal. Okay, and so this can be expressed in this way. Okido, so this is x xn. Okay, so first observation, you can immediately see from this definition of course, pay attention that this is just n, all this prefactor reduced to n, okay? So you immediately see that the diagonal part, what I said at the beginning, the diagonal part of this gamma, of course, this is the spin one body reduced density matrix, because I'm keeping the x, so there is also the spin variable inside. If you sum over the spin, you get the one body density matrix, okay? But I keep things more general. So you see, if you take the diagonal part of this one body, okay, this is precisely the density. You see, you get that x prime is equal to x, so this is xn, and you can write it like x, x2, xn square. And this is simply the spin density of your system, okay? You immediately also see that if you integrate over x, gamma x, you get back the total number of your electrons in the system, okay? Another relation that is important, because we will use it in the following, is that you have some recursive relation between between n-1 and n density matrices, okay? So you can express the n-1 density matrix, so x1, x n-1, x1 prime, x prime n-1, in terms of the n body density matrix. So there is a prefactor minus n plus 1, and this is the integral in the xn of gamma n of x1 n-1 xn, x1 prime, xn-1 prime, xn. And why is this important? It's important because, of course, you can apply it several times, and you can have a relation of any n body density matrix in terms of the density matrix with the small n equal to big N. But in particular, this is useful because we can express the one body density matrix in terms of the two body density matrix. So this relation you can immediately verify. So I'm not going to do it here. You can just plug in the definition of a gamma n-1 left, and here the definition of gamma n to the right, and you will see that this equality is fulfilled, okay? So in particular for the one body density matrix, you can express it in terms of the two body. This is equal to minus 2 plus 1 integral in dx2 gamma 2 x1 x2, x1 prime, x2, okay? So this is an important relation. So if you have gamma 2, you can get your gamma 1. So why all these are important? Well, because now from the definition of density matrices, you can immediately see that the total energy of your system can be expressed in terms of the one body and the two body density matrix, okay? So if I have the Hamiltonian in second quantization, as I have written just some slides before, and if I want to calculate the total energy related to this Hamiltonian, well, it can be expressed in terms of the one body density matrix. So it can be expressed like this. I will explain what I mean with this. x1 over minus blah blah r1 square over 2 gamma x 1 prime plus x1 plus then we have the external potential, so it's the integral in the x1 the x2 of v external x1 x2 gamma x1 x2. And then we have the electron-electron interaction that can be expressed in terms of the two-body density matrix, okay? So this is the Coulomb potential, okay? Actually, not the complete two-body density matrix, but just the one, R2, x1, x2, the diagonal part of it, okay? Okay, so now you see, I have this expression for the total energy. And since I know, I just show it here, I didn't show, I just wrote here that gamma 1 can be expressed in terms of gamma 2. Well, this the energy is a functional of gamma 2, right? It's a very clear, explicit functional of gamma 2. So then the question is, okay, but if it's a function of gamma 2, then we can minimize the total energy with respect to the two-body density matrix, okay? And use the two-body density matrix as basic quantity of our problem. So when we do this, this was also addressed in the FT, when we do this, we cannot just plug in this functional whatever 4-point functions that we want, okay? We have to put some restriction on the domain of definition of our functionals. Okay, this is defined for n representable gamma 2, which means for gamma 2, which correspond to a given an antisymmetric many-body wave function. Okay, now the complete set of conditions for a gamma 2 to be n representable were derived quite recently in 2012, but they are quite complicated to apply in practice. There are quite a lot of conditions and it's not clear how you can apply to minimize this energy, okay? What instead is simpler are the conditions for gamma 1 to be n representable, okay? So we have a choice. The choice is to have a very simple functional of gamma 2, but then it's difficult to apply the exact constraints for gamma 2 to be physical, or we have a functional of gamma 1 that is not completely clear because we have to show that this quantity can be expressed as a functional of gamma 1, but for which we have a simpler condition for gamma 1 to be physical, okay? And RDMFT makes the choice to work with gamma 1 as basic quantity and to apply simple condition for the energy minimization, okay? So, how do we do this? So, the basic theorem of RDMFT is the Hohenberg-Kohn theorem for non-local potentials. It was not demonstrated by Hohenberg-Kohn, it was demonstrated by Gilbert in 1975. And it's called Hohenberg-Kohn because Gilbert tried to do a similar demonstration as the one that Hohenberg-Kohn did for the FT. Now, Julien didn't go through this theorem, but okay, I want just to sketch it because at least you understand why RDMFT is essentially based on the same theorem, okay? So in the FT, okay, you have a local potential, local external potential, okay? This external potential enters in the definition of your Hamiltonian, so completely defines your Hamiltonian, okay? And therefore, through the diagonalization of your Hamiltonian, completely defines the eigenstate of your Hamiltonian. Now, if you look at the lowest energy corresponding to the corresponding lowest energy of this eigenstate, you will find the ground state wave function of the system. And through the definition of the density, okay, you get your density. So this simply says that your external potential uniquely defines your density, okay? Now, what Hohenberg and Kohn demonstrated is that it's also true the contrary. Of course, I'm speaking here about non-degenerate ground state, okay? So completely define your external potential up to a constant. It means that there can be various external potential corresponding to the same density, but they are just, the difference is just a simple constant, okay? So Hohenberg demonstrate precisely this, okay? So that in the FT, you have this famous one-to-one mapping between the density and your local external potential. And to do this, so if you look at this, you have that, everything okay?
Yes.
Okay.
Yes, everything's okay. Yeah.
Okay. So you have your external potential. So you have the map from the external potential to your many body wave function. We call it A. Then from the many body wave function, the ground state many body wave function, you have a map to your density. Okay, called B. And this is the full map F. So we said that Hohenberg can demonstrate that this is invertible. And to do this, they did the two steps. First, that A is invertible, and then that also B is invertible. Now, Gilbert tried to do the same for RDMFT. So for sure, if you have our external potential, RR prime, then this same arguments hold, right? It defines completely your Hamiltonian. So I have my eigenstate. I look at the ground state energy. I pick the ground state wave function of the system, and this through the definition of psi star psi of the density matrix defines my density matrix. Let me be more general, XX prime. Because can be also spin dependent potential here. Okay, so this is okay. So your potential will uniquely define your one body density matrix. However, this is not true. So the problem in the demonstration is that Gilbert realized that it's not due to the non-locality of your external potential. He didn't manage to demonstrate that this map is invertible. Okay, so this he didn't manage to demonstrate, but he managed to demonstrate that this map is invertible. So in other words, he managed to demonstrate that there is a one-to-one mapping between the ground state wave function of your system and the density matrix. And this is enough to set a one RDM functional theory, okay? So let's go through this part of the demonstration then. Okay. Yeah.
Sorry, can I ask you a question about this? Because I always wondered about that. So if you ignore the two electron repulsion, yeah. I perfectly understand that many non-local potentials can give the same density metrics, because they're always virtual orbitals that you can always move the energy levels, and then the density metrics will be the same. Yeah. But when the two electron repulsion comes into the game, yeah, I suspect that things will be different. So, so I cannot really see because all the orbitals will be in principle fractionally occupied. So I don't know, is it possible to explain this in simple words, or it's full of subtleties that I probably don't see? Or...
Okay, let's say that in the demonstration it's simple to see, because you simply see that you cannot, the demonstration does not demonstrate that it's not invertible. It's just demonstrate that, they don't manage to demonstrate that it's invertible, okay? But it was shown by some examples, I don't remember who, that in fact this is the case, that in fact you can have more than one potential that gives your density matrix. Now, how to see this, I don't know. How to explain this, I don't know.
Okay, but it's a non-trivial thing, right? As long as it's interacting, it's not trivial to...
No, precisely. So, okay. Yes.
Okay, thank you very much, sorry.
No problem. Okay, so for the demonstration. So suppose that we have two external potential, unprime and unprime, okay? And they, so therefore they define the Hamiltonian, unprimed Hamiltonian, and your unprimed, excuse me, your primed Hamiltonian. So the only difference is the external potential, okay? And then they generate two distinct wave functions, psi 0 and psi 0 prime. Okay, so now I write my total energy of the unprimed system as expectation value over my psi 0. This is the ground state total energy, okay? So now this is smaller than the expectation value of my Hamiltonian over the psi prime. And this is the case because psi 0 prime is not the ground state energy of my unprimed system. So it's like a trial wave function for the unprimed system, okay? So by the variational principle, I have that this expectation value is larger than the ground state energy, and consider that the two wave functions, they are distinct, so they are different, okay? Okay, now at this point I can, here, I write explicitly the Hamiltonian. Okay, so let me see. So what I'm going to demonstrate, so it's clear that to demonstrate the one-to-one mapping, okay, we have to demonstrate in both sense. So I have to demonstrate this, and this is I've already done before through this, through the definition of gamma in terms of psi, ground state psi. And now I'm going to demonstrate this, so the other way, okay? All right, so this is I have my Hamiltonian, right? So now what I can do, I can add and subtract the V prime, okay? Right, now what I do is to put together my kinetic energy operator, my electron-electron interaction, and my V prime, which defines my prime Hamiltonian. Okay, and then here I'm left with V minus V prime, the expectation value of V minus V prime. Okay, so this is equal. This is the total energy for the prime system. And here I have the expectation value over the psi 0 prime of this external potential. So now I can write explicitly the external potential in terms of the one-body density matrix, as I have shown you before. So I can write it like the x prime over V external x prime minus V prime x prime, and here I have the gamma prime x prime. Of course, it's the gamma prime because it's referring to the psi 0 prime wave function, okay? So overall, I have that this energy is smaller than the energy in the prime system plus this thing here. Right, now I can do the same, interchanging the prime and unprime system, okay? So if I do the same, I will have also here, so prime becomes unprime and vice versa. Prime, unprime, and this is the gamma x prime, okay? And now I can sum the two. So I have smaller than E0 prime plus E0 plus, and then here I have this, I put them together. So this is the same as this one with a minus sign in the front. And which multiply the gamma prime minus the gamma x prime. So of course, this is the same. So essentially I have that 0 is smaller than all this thing. Where the two external potential we said that are different, okay? So you see that not to have a contradiction, I mean the two gamma and gamma prime, that they cannot be the same. Otherwise I would have that 0 is smaller than 0, okay? So essentially you never have that given two psi 0 prime different between them, then you have a gamma that gives the same. No, this cannot happen, okay? So for each psi 0, there is, if I write like this, you see the other way around. For each psi 0, there is a corresponding gamma, okay? Which is what we wanted to demonstrate, which is not this that I wanted to demonstrate. Up and down. Okay, so this with the fact that we said that psi 0 itself define your gamma, I have my one-to-one mapping for non-degenerate ground state. So this is what we want. So it's a bit different from DFT, because in DFT you have also the one-to-one mapping between your with the external potential. Okay, so this simply means that the expectation value of any ground state operator can be expressed in terms of the one-body density matrix. Okay, so okay, so it's true that I can express my observable, in general, the expectation value of any ground state operator in this way. Psi 0 is a function of gamma. And in particular, the energy can be expressed for a given external potential, can be expressed as a function of gamma. Okay, so this is equal to this. Okay, plus V plus W. And this is equal prime. So this is the part which contains the kinetic energy and the external potential, plus the part that actually at the end we need to approximate. Right? So where H now contains my kinetic energy operator plus the external potential. Okay, so here I want to point out another difference with DFT. You see that at the end, so let's call it the W Oemberg-Kohn. That at the end, the energy function, there is a part that is completely known, that is the part related to the kinetic energy and external potential, okay? And so at the end, we will need approximation only for this part that contains the electron-electron interaction. This is a different, and this is one of the advantages to use RDMFT, is that in DFT instead, if you write your energy functional, you have the Oemberg-Kohn universal functional, and then you have your external potential. Okay, and this can be written as the kinetic energy functional, the kinetic energy of the quantum system, plus you have your R3 contribution, plus the exchange correlation contribution, and plus the external potential contribution, if you remember. And you see now, this is the kinetic energy of your quantum system that is not the kinetic energy of your interacting system. So this means that your exchange correlation the energy contains also correction to the kinetic energy. So in a way it's polluted by these corrections that you have to do to the kinetic energy. And this is not the case in RDMFT, because the kinetic energy is a non-functional of the one-body density matrix. Okay, so in principle, it's easier to find approximation in RDMFT because we have to approximate only the electron-electron interaction. Is everything clear? Well, if I don't have any answer, I guess so. If you have a question, just ask me. All right, so we have this energy functional, and this is similar to now to the FT. We have a variational principle, okay? So essentially what we have is that the ground state one-body density matrix minimize your total energy, okay? So if we have, suppose that now we have a one-body density matrix gamma, which correspond to an external potential V unprimed, and a gamma prime, which correspond to V external unprimed, then if I write my total energy as functional of gamma prime, so it means as expectation value over psi zero functional of gamma prime, okay, this is by the variational principle bigger or equal, if the two gamma are the same, bigger or equal of the expectation value over psi zero as function of gamma, where gamma is the gamma corresponding to the unprimed system. Okay. Right, so this means that to find the ground state energy of our system, we have to minimize over this set. I will explain what I mean for this set of density, one-body density matrix. We have to minimize our energy functional action. And this is what I have written before. Okay, so I have to minimize this. Now, this set of density matrices is the set of pure state V representable density matrices. So density, one-body density matrices which correspond to some given external potential. This is similar to the FT.
Ina?
Yeah.
Since you talk about it, there is an interesting question. So I read the question. Is there any relation between Kohn-Sham density matrix and the interacting one? And can the Kohn-Sham one be a good approximation to the interacting one?
I will answer in a moment, because I will speak precisely about the existence or whether a Kohn-Sham system exists or not. Okay, thank you. And then maybe you can reformulate the question, because I don't know if I answer your question. So just in a moment, it's good. Because, okay, so yes, so you have to, as I said before, for gamma 2, is not that you minimize over whatever two-point functions. So you have to restrict the domain of your functional, and this is restricted. So this functional as domain the set of one-body density matrices which are V representable. Now, as in the FT, the condition for one-body density matrix to be V representable are not known. So how do we solve this problem? Well, in practice, also here, we extend the domain of applicability of our energy functional, and we minimize over the set of so-called ensemble and representable densities. So I'll come back in a moment to this. And here's the question on the consham. Okay, so far you see we are following more or less the same strategy as in the FT. Okay, we have some one-to-one mapping. We can express our observable in terms of our density matrix. We have the energy function, we minimize, blah. At this point you say, okay, what about the consham system? I mean, can I have a consham system also for one RDMFT? So just a reminder, so in the FT, what do we have? In the FT, we have our system of non-interacting electrons, okay, in some external local potential. And they have a certain density. Again, now I speak about charge density, okay? I integrate it over the spin. And then we have this beautiful system, the consham system. So this is the interacting. And then I have my consham system. Okay, I have a system of n particles that do not interact, moving in some potential that I call consham, local. Okay, and this potential, what does it do? It has to do only one thing. It has to produce a consham density that is the same as the one of the interacting system. So this is what it's doing, okay? So now the question is, okay, can I have something similar also in RDMFT? Right? So now I have an external potential, which is non-local. I have again my interacting system, okay? And here I have a certain density matrix. I think it's simple. Simple, simple, simple. Okay, so does it exist a system of non-interacting particle moving some non-local potential? Okay, such that now the density matrix is the same as the density matrix of the real system. Can it exist? So to answer, so I think you will answer this question in a moment if you follow my argument. So first of all, the one-body density matrix is an Hermitian operator, so it can have, it has real eigenvalues, okay? And I can express it in terms of its spectral representation, in terms of its eigenvalues and in terms of eigenfunctions, okay? So these eigenfunctions of the density matrix are called natural orbitals, and the Ni, the eigenvalues, are the natural occupation numbers, okay? Now, I want to show that if you have as a wave function a Slater determinant, then these occupation numbers are either 0 or 1, which are quite different from an interacting density matrix in which the occupation numbers are fractional, okay? And this can be seen in a simple way, doing just a simple exercise. Now we calculate the density matrix corresponding to a 2x2 determinant, a Slater determinant, okay? So I take my Slater determinant, my wave function x1, x2, okay? I write it in terms of Slater determinant built from the eigenfunctions of gamma 1, okay, from the natural orbitals. So this is equal to 2 factorial, and then I write my phi 1 x1, phi 2 x2. Yes, completely phi x1, x1, x2, phi 2, x2, right? Okay, boom. This is equal to this. So I calculated the determinant now. Right, and now I want to calculate the corresponding density matrix. So my density matrix is equal to, I take the definition, I have n as prefactor, so n is equal to 2 in my case. Then I have an integral over, starting from x2 up to xn, but in my case, n is equal to 2, so I have just the integral over x2, okay, of psi star x prime x2, this is just the definition, okay, x2, right? Okay, now I substitute the Slater determinant inside. So the prefactor here cancel this prefactor 2. Okay, so I'm left with the integral over 2, and then I plug here the Slater determinant. So I have 1 x prime. I have to be careful to put at the place of x1 x prime. Are all star here, x2 minus v1 x2 v2. There's a little mistake here, 1, okay. Voila, this is all star. And then I have the other one, so I put this x2 minus, right. Okay, at this point, you see, I have some products here of 4 wave functions, and I have this integral. So this integral will couple, essentially, will give non-zero contribution only when I integrate over the same wave function. You see, now I have x2 here is the same because the natural orbitals are orthonormal, okay? So this gives me a contribution that is non-zero, this as well, because I integrate over x2, and x2 is in the same orbital, while terms of this kind, they will be 0, right? Because x2 is here in phi 1 and here in phi 2, so the integral will give us 0 because they are orthogonal, the orbitals. So I'm left just with the 2 product which survive. I have this times this, so it's this one, all right, and then I have this times this, okay, plus and this can be written in a compact form as the summation over I of phi I x prime. I have something left, so it's star, and this is star. Okay, so okay, and you see, this is just the spectral representation of my gamma, in which now the occupation numbers are 1, okay, when they enter here, and are 0 when they are not occupied. They have to be 0 because they have to sum to n, the total number of occupation numbers, okay? Right, so what we saw here is that for this simple example of Slater determinant, the occupation number are 0 and 1 are not fractional, and this is something general for the Slater determinant. Actually, you can say that your one-body density matrix is idempotent. So it means that if I have my density matrix, okay, this is equal again to x prime. Sometimes it's written simply like this is idempotency. Okay, and when this is the case, okay, this means that your occupation numbers are 0 and 1, and you can prove it in a simple way, just plugging in the spectral representation left and right. Okay, so here what do we have? I put the spectral representation of gamma, so I have summation over I n I phi I. X phi I star y. Then I do the same for this other gamma, summation over j of phi j y phi j star x prime. And this is equal now, summation of ij n I n j integral in dy of x put together phi j star x prime, and then I have this and this I can make it up here. So the integral over y of these things will give us a delta ij, and overall all this becomes this j I star x prime. Okay, so on the left-hand side now, this can be expressed in this way. On the right-hand side, well, I simply put the expression for the spectral representation. X prime. And you see, this means that your occupation numbers, I square, are equal to Ni. And this can happen only when the occupation number are either 0 or 1, okay? So actually you can show that the density matrix, the one-body density matrix is idempotent if and only if your wave function is a single slated determinant. Okay, now, knowing this, let's put the things together, right? So we have a slated determinant. Occupation numbers 0 or 1. Consham system. The Consham system, what is the many-body wave function of a Consham system? The Consham system is a system of non-interacting electrons, so the many-body wave function is... Somebody can answer. Not the teachers, not Julien. I don't see you. So it's a slated determinant, okay? So can a Consham system exist for RDMFT, considering that the Consham should give me a gamma Consham XX prime, which is equal to the gamma of the interacting system? So please give me an answer. At least the person who asked me the question. Okay. Okay, so the answer is no, okay?
Yeah, that's what the person wrote, actually. Yeah.
You wrote, sorry, because I don't, but why don't you speak, just speak to me, because I don't see the chat person who asked me the question. I don't.
Someone just answered now. They said, okay. No, it cannot. And actually, if I read the previous question, yeah. the person who asked guessed already that an idempotent density matrix was an approximation. So it was,
so it means that I didn't explain so bad the things. So if
no, doesn't it like?
Because I don't see I just see my whiteboard. I don't see.
Yeah, no, I keep on keeping an eye on the chat box. Don't worry.
Okay, very good. So yes, so to all of you who guess the answer, yes, the answer is that cannot exist. Okay. And therefore, we will live with this. I mean, it's not a big problem. It means simply that we don't use a Consham system to calculate our one-body density matrix. Okay, what we do is to minimize our total energy to get our one-body density matrix. Okay. Okay, perfect. I have another hour. So let's go back then to the, so this is, of course, I mean, together with the fact, I mean, with the story of the kinetic energy functional, that in RDMFT is a known function of the one-body density matrix. Together with this, the fact that it does not exist a Consham system is another difference, of course, with the FT. Okay, so we go back to our dense energy functional, and we wrote that this should be the ground state is found as the infimum of gamma over a set that I called like this, you know, of n representable, and actually it's pure state n representable density matrices. Okay, so let me take it back, the expression. Yes. Okay, so it's this one. So as I said before, the condition for gamma to be representable are not known, but actually what are known are a set of very nice conditions that are very easy to use, and are the condition of ensemble and representable density, one body density matrix. So what do we mean for ensemble? Okay. So first of all, gamma ensemble. Gamma. So gamma is said to be ensemble and representable if we have a set of what we call pure state. Pure state is what we have used so far, essentially, our state vector in the Hilbert space. So we don't call a pure state because so far we didn't need to define mixed state. So now we will call them a pure state to make a difference with the so-called mixed state. Okay. So ensemble and representable. So gamma is ensemble and representable if we have a set of pure state with a set of weights such that these weights, they sum to 1, so that we can express our gamma x prime in this way. Okay. So this is what we call for ensemble and representable gamma. And the condition for a gamma to be ensemble and representable, they are simple because are only these two. The fact that the summation over ni is equal to n, and the fact that the occupation numbers are between 0 and 1. Okay, so these two conditions, they, well, the first is essentially related to the fact that the total number of particles is n, okay? And the second is related to the Pauli principle. The principle, you cannot have more than one electron for spin orbitals, okay? So these conditions are sufficient for a non-degenerate ground state, are sufficient to guarantee that the minimizing one-body reduced density matrix correspond to a pure state, okay? When we use the exact functional, okay? So even if we now minimize over a larger set of density matrices, which is the set of ensemble and representable ones, the minimum is found at the one that one would get from a pure state minimization. Okay, this at least, as I said, when we use exact functionals, which never happen, of course. Okay. Of course, they are also what we call the pure state and representable condition. These are called generalized Pauli constraints, and are very complicated because are condition that depends on the number of electrons, but also on the dimension of the Hilbert space. So it depends on the number of natural orbitals that you are using, and it grows, explodes essentially. The number of conditions that you have to use explode with n and m. Okay, so in practice, it's very difficult to apply for a many-body system. I mean, you can do something for 3 electrons, anyway. But it was proved, indeed, that when you have approximate functionals, it's not you can have 2 different answers if you apply the ensemble representable and representable constraints, and if you apply the pure state and representable constraints. Okay, so this is to keep in mind. So now, we have these constraints, and what we do? Well, we minimize the total energy. So now, I didn't speak yet about approximation to this thing, okay? But I will do in a moment. And I must say, anyway, I want to say here at this point that in general, approximations are explicit functionals of the occupation numbers and natural orbitals, and only implicit functional of gamma, okay? So in general, the minimization is done with respect to the occupation numbers and natural orbitals, okay? And the constraints, therefore, that one uses are the n-representability constraints, so the ones that I've just shown, right? And then we put constraints on the fact that the eigenfunctions, they have to be orthonormal. So this actually is very similar to R3-Fock. This is very similar to R3-Fock. When you introduce, you minimize your total energy with the Lagrange multipliers. We do the same here, and here we have to impose also these other constraints. Okay, and so what do we do? Well, they can be introduced, as I said, with the Lagrange multipliers, and these, okay, there are several ways in which we can do this. And a clever way I like this is to express the occupation numbers in terms of the cosine square, and to let theta vary freely, we don't care. And in this way, you will have occupation numbers between 0 and 1. Okay, so at the end, the functional that we have to minimize is the energy functional, but with these constraints. So it's a functional of theta and the occupation, the natural orbitals. So it's the energy function that I have just shown you before, which is, let's say, is a function of theta. Minus, and then we introduce some constraints. So it's the first constraint is the constraints over, is this one, okay? No. Minus n. And then we have the constraints over the eigenfunction, okay? So j, which multiply phi I, phi j minus delta ij back. Okay, so at the end, what we have to minimize is this, and the minimization is with respect, as I said, to occupation numbers and natural orbitals. So this is a bit different from, for example, R3-Fock. Okay, but in DFT we use the Consham system, but in R3-Fock, when you minimize your total energy, you don't have the constraints over, at least I think so, over the occupation numbers. Okay. Now the point is, okay, we minimize this total energy, but at the end there's a part of this function that we don't know, so we have to find approximation to it. Okay. So how do we find approximation? Let's go back to this. Originally, you remember I have written this in terms of gamma 1 and gamma 2. Okay, so we have the total energy. So let me write in this way. Okay, I don't have to explain anymore what is this, kinetic energy, external potential, plus, and then there was this other part of the Coulomb potential, you remember. So now we know that gamma 2 is a functional of gamma because of this Hohenberg-Kohn theorem. So the question is, how do we find approximation to this? Okay, so this is what I've written before as is the same thing. It's just different notation. It's the same thing. Well, gamma 2 can be written in terms of various contribution. Okay, so there is a part that we can call I don't know, uncorrelated part. Okay, which can is a part that in which gamma 2 can be factorized in terms of gamma 1. And there's a part that you cannot factorize, and that we call correlation. So the correlation part of gamma 2 is not really gamma 2, right? It's just the diagonal part of it. Anyway, so if you neglect this, you get your R3-Fock gamma 2, okay? So in fact, if you plug in this expression of gamma 2, this approximation of gamma 2 in your total energy, okay, for the interaction part, you will have two contributions. The R3 contribution, which is integral dx prime bc r prime gamma x gamma x prime. So you see, this is your density, and this is therefore your R3 energy. Okay, and the same for the exchange. Okay, you plug in this part. Gamma x prime, gamma x prime x. And if you cannot recognize your R3-Fock total energy, it's enough for you to plug here and here the spectral representation of your gamma 1 when you have an R3-Fock wave function, which is a slit determinant, okay? And therefore Ni is equal to 1 or 0, and therefore we can just write this. Okay, so if you plug in this expression for your gamma 1, you will find back your expression of the R3-Fock total energy you are used to. Okay, but you can write it also in this way, in this more compact form, without using the one electron orbitals. Okay, so this is R3-Fock, and this is an explicit functional. R3-Fock is an explicit functional of the one body density matrix. Okay. Now one can go beyond R3-Fock and to try to include some correlation. And I want to speak about the work of Mueller, because essentially a lot of functionals, they have built on the function of Mueller. So what Mueller does, this is also an explicit functional of gamma 1, okay? So Mueller essentially wanted to keep the same shape of the R3-Fock gamma 2, but put some correlation. And what he did is to then write something like this. So I write it in a general way for the 4-point gamma 2 is the same thing. Okay, so this is the part which will give you the R3. So let's keep things simple, otherwise you get confused. X2, X2. And then what he did is this. So introduce an exponential. Okay, and doing this, he found that actually this form, so you cannot keep the R3-Fock form and introduce this exponential because it violates some physical constraints of gamma 2, such as the fact that gamma 2, x1, x2, must be equal to or bigger or equal to 0. Well, using this form with this P, he found that this was negative, okay? And this is not very physical because it's, essentially this is the probability of finding an electron at R with a spin, with a certain spin, when you have another electron at R2 with another spin, so cannot be smaller than 0. And he found that this was 0, and he tried to minimize this error, and he found that the best exponential to minimize the error was P equals 0. Okay, so you get your Müller functional, that is the minimal error that you can commit on some of the physical constraint of gamma 2. So this is your functional. Okay, so what does it mean, this exponential? It means that when you write your gamma, the gamma in terms of the spectral representation, this exponential, okay, it means just this. Okay, so this is the Müller functional, and in general what you find is that the Müller functional overcorrelates your system, puts too much correlation in your system. I introduced the Müller functional because there are many functionals which are built on it and essentially are called, so if this is the Müller, the so-called JK functional, that have all the same form and can be written in this way. So for the exchange correlation part, so it's the interaction part beyond the R3, okay, can be written in this way as I said, functional instead of the natural orbital, excuse me, occupation numbers and natural orbitals, okay. And this like this, let me see on my notes, and J and K, and then I'm left with all the, all right, so this is the final expression, and you see that when your, so these are the JK functional, when your F is equal to N, J, and K, you have the Hartree-Fock form. Of course, now you have NJ and NK, because in general, the one-body reduced density matrix as fractional occupation numbers, okay? If you don't put correlation in your system, they will be 0 and 1. But if you put also correlation, I mean, also the Hartree and the exchange part, they will have these occupation numbers that are fractional. And then, for example, you get back the Müller when this is equal to this. Okay?
Dina, can I ask you a question about the Müller functional?
Yes.
So when you discussed about the P parameter, so now in your formula, if you replace the 1/2 by just 1, you get back to Hartree-Fock, right?
Yes.
Okay. So I was just wondering, because so it means that moving from 1 to 1/2, you incorporate correlation effects in the functional, right?
Yes.
So there are different degrees, like for example, if you take the Müller formula and you plug in the Hartree-Fock density matrix, you recover already some correlation, right? Because there is a functional and there is the density matrix you give to the functional.
No, but if you put your Hartree-Fock density matrix, it will have occupation numbers 0 and 1, right? So your exponential 1/2 will not do anything.
Okay.
Yes.
So you really need a correlated density matrix to get something out of it.
Yeah. So essentially, you can put whatever exponential you want. If your occupation numbers are 0 or 1, you get Hartree-Fock.
Okay. And the 1/2, so if you vary this exponent from 1 to 1/2, you said that basically this is the best physical choice, and in between it doesn't make much sense, right? Or...
Yes. So I mean, P, yes, indeed, because so let's say that if you set P equals 0, is you do the mean. It's the less worse approximation that you can do because you violate less this condition on the gamma 2.
Okay.
So if you choose something in between, you will violate more this condition. But you have functional that do precisely this, they have in between, and they don't care about this violation. For example, the power functional is one of these, and this essentially, so, I mean, there's also an explanation there. So this is the Mueller, and then you can have the power functional that you say, okay, I put an alpha, so it's my nj and k, I put an alpha here, okay, and this alpha, it's between 1 and 0 and 1 alpha, okay? Sorry. So the idea is the following. So I have Artifock that has no correlation at all. Okay. Then I do Mueller, and it correlates too much, over correlate, and then I try to do something in between. Okay. And so this alpha, yes, this alpha. Okay. Anyway, I mean, actually, I must say that I work with this alpha, and it's for solids. I mean, it's. I mean, for solids. The only functions that are used are basically these JK type functionals, because more advanced functionals are quite difficult to implement, especially because more advanced functional, they try to couple natural orbitals. And when you go to solids, it's not clear how you have to couple, because you have more than one K point. It's not as simple as in molecules. You have more than one K point and you don't know what to couple, essentially. So now maybe it's, for students, this doesn't make any sense. But let me say that even if this power functional violate, when you go far from 1 alpha, violate this condition, anyway, I mean, can be, I mean, it's used in solids because it's the best that you can do. Let's put it together. Okay.
So there is actually somebody who wrote a question, so I'm going to read it.
Yeah.
So is this Müller correlation come from the hope that the Coulomb interaction is strongly modified by the effect of other charges? In many body perturbation theory, we talk about screen Coulomb interaction. So is there any connection with the screening?
That's a very interesting question. I like this because essentially what you have is that when you put this, let's say this alpha, okay, so the Mueller, whatever. So you see that indeed your occupation numbers become fractional, while in Artifock they are not, okay? If you want to do the parallel, for example, with the GW, so with the screen interaction, okay, you will see that you can get fractional occupation numbers only if your screening is omega dependent, okay? So the fractionality that you get with the Mueller functional is more related to the dynamic, according to me, this is my interpretation, but with my work, I see this is more related to the dynamical feature of your screening and not to the static screening itself, okay? So the static screening doesn't get you fractional occupation numbers, while dynamical screening, yes. And so the Mueller, or all these alpha, which are fractional, they can be related to the effect of the dynamical screening.
Okay.
I don't know if I answered your question.
It was not my question, but I understood what it is. Maybe one last, so among all these functions you're talking about, is there any one of them is exact for 2 electrons, for example, or? The
Mueller is, okay, there is the loading shell functional that should be exact for 2 electrons. But for example, the Mueller is exact for the Hubbard dimer with 2 electrons. So H2 minimal basis set local interaction is exact.
Okay.
Loading a shell should be exact for the 2 electron case.
Yeah. Okay. Yeah. Okay.
Yeah. And then, okay. So I mean,
no more questions for the time being.
No, I'm just deciding. So, I mean, I don't want to spend so much time on the function. So, of course, I mean, once you have this, you can do many corrections to it. But as I said, I will stick to JK functional. And there were other correction to this, such as, for example, remove self-interaction, such as, for example, this was done by Bowes and Barents. They improve the Mueller functional, making a separation between weakly and strongly occupied orbitals and between bonding antibonding. So you can do many things as variation and improve the results. Okay. What I want to discuss now is about some properties. So we do all this. We set all this, okay, the RMFT, or Oemberg-Kohn, blah, 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 we minimize, okay, we get our density matrix, and then, and yes, okay, we get our total energy, and then what? Can we get some other properties, okay? Well, well, of course, I mean, you can get your ionization potential doing total energy differences, okay? So if I define my first ionization potential as the difference between the ground state energy of my n-electron system and the ground state energy of my n-1 system, okay, I can get to this IP, okay? And the same for the electron affinity. I can do something similar. I can do these total energy differences. And not always this is possible. First of all, not always you want to do 1000 total energy calculations. Not always this is possible because you can have unstable systems. And anyway, for solids, this is not very practical. Okay, because you have to add an electron where. Okay, so what one can do is to use a theorem which is called the extended Kupman theorem, from which you can get within RMFT ionization potentials. So not only the first one, so all the valence removal energy, and you can get also actually addition energies. And the extended Kupman theorem is exact for the first IP using exact ingredients, okay? So I don't know if, I will go, what is this? At least to give you some, the basic equation of this. So let's look at the removal part of your spectrum. So now we look at the ionization potentials, okay? So in other words, valence energies, okay? So we start from the definition of this, as I gave before. So I have my an electron wave function, okay? And I calculate my energy, total energy, and then I need this, okay? So I can approximate this in this way, and I'll explain in a moment, okay? Up. No. Psi n, then I have to up. So what I'm doing here, so I have my my operator, okay. So it's an approximation. So essentially, I want to find approximation to this total energy, where now you see I have generalized. This is not just the first IP. So this is just E0n minus E ni n minus 1. Okay, so I want to get all the IPs here. Okay, so I define my operator in this way as a summation over I of Ci ni of E. This is the destruction operator, and essentially I approximate my n-1 wave function acting on the psi 0, so acting on the n electron wave function and removing electrons from several orbitals, okay? And for the creation, I have this is a linear combination of the creation operators. Okay, so I'm approximating essentially my psi n-1 ni in this way. okay, in this way. Right, so this is the definition of my then energy which comes out, and this can be written in a more compact form. You see, I can write this in this way. So this is just the energy. Oh, sorry. Okay, I can multiply this here. I feel that I don't have so much time, so I don't want to, sorry, this is a mistake, get lost in the derivation. So I want just to sketch fastly. Yep. Psi n, this is h. So this can be written in this way. Over this. Okay. And then you see this can be, in fact, expressed in this way, psi n, n of h psi n. You see, I mean, now I connect h on the right, and I get my total energy. Okay, so I can express this first part in this way, and this is nice because now I can write all this in a compact form in terms of commutators. Up. Okay, so the first part, excuse me, the numerator can be written in this way. And then the commutator between the operator O and H. And I have some, yeah, it's okay. Okay, so I have my energy expressed in this way. And you see in O, there are this coefficient, and this coefficient are optimized by minimizing my epsilon n, which correspond to find the best psi n minus 1. Okay, so writing the stationary equation with respect to the coefficient C, one arrives, I cannot go through all the derivation because I don't have time, but one arrives at this secular equation, which is something like this. Equal 0, where these are matrices, and this has this expression inside. So it has just, I'm copying from my notes because I don't know, I cannot remember by heart this expression. Okay. I, yes, so psi n. Okay, this is this, and the and S is just the density matrix. So this is simply density matrix that we have just defined. Okay, And so what you can do is to solve essentially this equation. Now, what is the relation between this equation and RDMFT? The relation is that if you plug in your Hamiltonian in second quantization and you work out this Hamiltonian, you will find that this circular equation can be written in this compact form. You have a lambda matrix that you have to diagonalize, okay? So this has been obtained in different ways by several authors. Okay, I did here with the extended Kupman theorem, which is quite general. You can apply also to other theory, not necessarily to RDMFT. And so you arrive at this equation. Okay, so here are the matrix element of the Coulomb interaction. These are the matrix element gamma 2. It's not important how we define them. And these are the matrix element of the one-body operator. And you see that if you diagonalize this matrix, then you get your eigenvalues, which are the original epsilon B. Okay, so you can get your IP. So there are two sources of error in this, of course. The fact that the lambda itself, it's an approximation except for the first IP. For the rest is an approximation, and the fact that in practice we use approximation for gamma 2. Okay? But you can get out this IP. And you can do something similar also for the addition part. So there's a corresponding lambda addition, and you can get also your electron affinities. So this is usually is not used in solids because it's thought to be too heavy, although we are actually doing it. And in principle, you can get also the band gap from this equation. Okay. So this is only about ionization energies, so ionization potentials or electron affinities. Okay, I'm not speaking about spectra. I'm not speaking about the weight of these energies. We will come there in a moment. So since apparently for solids very heavy to diagonalize this matrix, so some in the group of R.D. Gross, they did some approximation to this lambda. So what they thought it was to express. So this is one way. Another way to express IPs and electron affinities is to think a little bit in terms of like Cookman's theorem. Okay. Although for RDMFT is not completely justified, but the idea is the following, that we can define removal or addition based on their position with respect to the Fermi energy or the chemical potential in this way. So when I do the RDMFT calculation, I get my total energy as a functional of occupation numbers and natural orbitals, okay? So I have this and this. So now what I can do, I take everything fixed to the optimal values, so the values which minimize my total energy, except one. So I take the kth orbital and I set it to 1, okay? Then I take the same functional with all the optimal values fixed, and I put this nk to 0, okay? And this defines my removal or addition energies, okay? So this can be further approximated if the total energy is linear in the natural orbitals. This can be further approximated as a functional derivative with respect to nk at nk is equal to 1/2. And you get this by Taylor expanding your total energy in natural orbitals around n equal 1/2. So it's a clever approximation, and for solids, for example, the removal addition energy are calculated in this way. It's a way to calculate them, okay? Now, at this point, in the last 20 minutes, I want to make a connection with the Green's function, because so far, I mean, I have spoken about ionization potential, electron affinities in an approximate way. Okay, I show you that in general, what we can get from these methods is something approximate. even using exact ingredients, because the observable itself is an approximation, okay? If we are interested in charged excitation, so removal and addition energy, the best way to get them is from the one-body Green's function that will be introduced by Xavier Blase next week. But let me, since otherwise you forget about the body density method, so now it's the right moment to make the connection with the two. So what do we have? So first of all, I can define, as for the n-body density matrices, I can define also here some n-body Green's function, okay? So I have something pretty similar, but more complicated, of course. So I define in this way. So first of all, this is not correct. N prime, okay, and this is defined as in this way: the expectation value of some field operators So I will explain in a moment what are all these. Oh no, low battery, shit. Wait a moment. Okay. Sorry about that. Okay. Okay, so this is the definition, and I will explain in a moment. Let me remove this. All right. Over this, well, we always put this, but at the end we can assume psi 0 to be equal to 1. Anyway, so we have this definition. So what do we have here? So you see already some similarities, no? There are a bunch of field operators, the creation and annihilation operators, and so it's very similar to the n-body density matrix, but we have something new. First of all, all the indices, they don't include only the space and spin variable, but they include also the time. And then we have this operator, that is not so innocent, because actually, it orders the times, okay? So it gives you several ordering of these operators based on their time, okay? Ordering to the left, the later times, okay? So only one of these orderings is the one that will give us, for example, that will give us the gamma n. Okay, because we have to put the operators in such a way that we get the definition of gamma n. So the n-body Green's function has much more information than the n-body density matrix. In particular, to make things simpler, we have the one-body Green's function, which is the quantity of interest for the ionization energy and electron affinity, which is defined like this. So for simplicity, I consider this normalized. So I have this. And here also I forgot to say something important. So what is this H here? This H simply means that we are working in the Heisenberg picture. So these field operators, you see, they have also the time inside. So for example, something like this means that we have this, this expression. And similarly for the upside dagger. Okay, so this is the one-body Green's function. And then you see now we have this time ordering here that can give you two orderings of the times. So if I concentrate just on this time ordering, So I understand that after 2 hours of lecture, now start with the time ordering is a bit, I don't know if you will manage to follow. Anyway, you will have next week to understand better. But I want to show you that indeed it's true what I said at the beginning of the lecture, the fact that the one body density matrix is related to one part of the G, okay? Because now you can have 2 time orderings. So when I can have either this psi dagger, when T1 is bigger than T1 prime, or I have minus, now I have to interchange them. So due to anti-commutation relation between the field operators, I put a minus sign, okay? For T1 prime bigger than T1, okay? So I have these 2 time ordering, so overall my G can be written in an explicit way. So mathematical, how do I write this? The two ordering of the times. I can use some theta function, okay? So I can use some theta function. So when my T1 is bigger than T1 prime, this theta function is 1. So I can have this ordering. Okay, and then when my T1 prime is bigger than T1, I have this other ordering. Now, look at this. This is precisely what we like, because this is, in principle, a gamma almost x1 prime. When do we get this? Well, we get this when we get rid of the 2 times. Okay, how we get rid of this? Well, if you write this explicitly, you will see that this is equal to T1 prime minus T1. And now I plug in this definition here. So I have my psi 0, I H T1 psi dagger x1. Then I have minus Ci, excuse me, is T prime. T prime, and then I have my T1 psi x, so this is 1 prime. Yes, up, and then I have EHT1, everything on psi 0. And now I like this because now I can act left and right here. Okay, so I get my E. Then I have here, I have my E, psi 0 is an eigenstate of H, so I have 0 T1 prime, and the same here, it acts here with my T1, so I get minus IE0 T1, okay, so I have just this, all right, and then I'm left with psi 0, psi dagger x1 prime, I have something here in the middle, and then I have my x1 on psi 0. Okay, so when T1 prime is equal to T1 plus, okay, which means that I only select this theta function and not this theta function, okay, I get back my density matrix, because here goes to 1 the exponential, this goes to 1, and I'm left with the definition of density matrix. And it's precisely the fact that I get rid of the time that I don't get explicitly my charge excitation, okay? It's precisely this dependence on the time difference that will give me the charge excitation directly from G, okay? So I have 10 minutes, so I can show this in a hopefully simple way. So how do we get this charge excitation? We write explicitly G in this way, where tau is the difference of time, T1 minus T1 prime, okay? And what I do now You see, I have these two parts of my G, and what I do, because I want to get rid of this exponential here in between the two field operators, what I do to get rid of this is to insert a complete set of state in the Fock space. Okay, the Fock space is a collection of Hilbert space in which your particles, they change from 0 to 1, okay? Okay, and if I do this, what do I get? So I can write like this, summation over M, psi 0. Okay, so now I insert my complete set of state, and okay, the only ones which will survive, of course, the number of particles can be, as I said, from 0 to n, but the only one which will survive for here are the ones with n plus 1, okay, because you have your field operator which will destroy a particle, and then otherwise, I mean, vector state with a different number of particles, they are orthogonal, okay? Okay, so we have this, then we have this, psi 0, and then I have the same thing here. I don't need to go too much in details because you will have your lecture on this, okay? This, the same thing, the only states which will survive here are the one with n minus 1 particles, okay? Because this creates a particle, so I have n particles, xt, m psi 0. Okay, now I have all these, and I can work out this Heisenberg picture here, as I did before, okay? So, as Xavier will show you, if you do this, I guess, if you do this, so if you explicitly write your field operators, as I said before, in terms of in the Heisenberg picture, HT, okay, then you end up with something like this. Let me write it. So you have minus E theta summation over M psi 0. Okay. X prime. And here I have the exponential which come from precisely acting this exponential that are here on my ground state energy and on the, ground state wave function and n plus 1 wave function. So I have this and then I have this. N minus 1, n, and then I have this x, and then I have psi 0, and then I have this exponential, okay, 0 n minus n minus 1 theta. Okay, now this is your one-body Green's function, okay? The fact that I write tau, because you saw that writing explicitly the G, you see that only time differences appear in the expression on the right-hand side, okay? So this is my one-body Green's function. You have here this exponential. You have precisely what we want. These are electron addition energies, and these are electron removal energy. So when you go to Fourier space, if you do a Fourier transformation of your Green's function from time to frequency, okay, you end up with this simple and clear form of your G XX prime omega. Okay, we always take this little eta to avoid explosion up. and you can write it in this way. So I don't want you to understand all the steps here. What you have to understand is that why the one-body Green's function is the best quantity to calculate removal addition energy, because they simply appear very naturally in its Lemon representation, okay? Then the question is how we calculate the one-body Green's function, because this that I gave here is just the exact expression, okay? But this is another problem. Okay, minus I eta. And if you define your spectral function, xx prime omega as 1 over pi, the imaginary part of the the absolute value of the imaginary part of your g xx prime omega, you will get your spectrum. What is the spectrum? Is strongly related to photoemission spectra, which is what you measure. You have your removal and addition energy with some weight. Okay, so it naturally comes using the one-body Green's function, and it's not so natural in RDMFT. So in RDMFT, if you want to use it, you start already with an approximation to your observable, and on top of this, you have to add also approximation to the exchange correlation energy functional to calculate your one-body density matrix. Okay, I think I'll stop here. If you have any questions.
Well, can I ask a question?
Yeah.
About the extended Kupman's theorem. So now you just have shown that if you use the Green functions, you can make it somehow exact. But I was wondering if you decide to remain in a completely time-independent framework, like in regular RDMFT.
Yes.
So can you make this theorem exact by introducing some function of something, or you really have to move on to Green functions?
The theorem is not exact. So the extending Kupman's theorem is not exact. You can
that's my question.
Yes. So you can show that it's exact only for the first IP with some arguments, let's say, and it was also proved numerically. Okay, if you want to improve over this, you have to extend the essentially you introduce in your expression also gamma 3, gamma 4 correction, high order correction, because now in the way in which we write it, if you look at the expression that I've given, you can reformulate the extended Kupman theorems in RDMFT, and it only depends on gamma 2. Okay,
so
you can put correction to it, and it will be gamma 3, gamma 4, for example. Essentially, you put correlation to the observable, actually, to the observable.
And the coefficients that you optimize variationally, you said. So this gives you at the end some kind of approximation to the Dyson orbitals, or?
Yes, yeah, yes. Yeah. So in fact, you can, so now the EKT, I use it for the IPs and electron affinity, but you can also write within RDMFT the spectral function, okay? And so you start from the expression of G, and you approximate the numerator of G, which are the Dyson orbitals. The numerator of G are the Dyson orbitals. You can approximate with this extended Kupman's theorem, and you can have the full spectral function, which is even with the exact ingredients, is still an approximation.
Okay, I understand. Okay, thank you very much.
No problem.
So I don't see any questions in the chat box.
They're still alive. Everybody's still alive?
I think so, yeah. People are connected, so.
Because I don't see, wait a moment. Okay. Okay, then I don't know.
So. Well, I guess we say bye-bye, or yeah, no more questions.
No, I think these are just all comments.
Yeah.
Okay.
Okay, thank you, Pina. Thank you very much.
Thank you, Pina.
No problem.
So,
okay, I will send some lecture notes so you can upload.
Yeah, then I will upload them on the website.
Okay.
The video. Okay.
Okay.
Thank
Bye.
you.
Bye. Bye.
Thank you. Bye.
Bye.
Grazie.